the channel. So in this lecture we are going to have the star or Y connection and the different terminologies related to it. Okay. In the previous lecture we have seen that what is the three-phase AC connection, what is the conditions for balance system, what are the phasor diagram and so on. Okay. So now we are going to have the star connection. Before getting into the star connection and different derivation for the relations, we will have that what are the different terminologies we are going to use. So there is nothing new terminologies. The terminology is same, whatever we have seen for single phase AC circuit. Okay, but because we are working on three phase, so here we will have two new terminologies, that is called what? Line quantity and phase quantity. Okay, so we will have two new terminologies, that is called line quantity and phase quantity. Okay, so what is this line quantity and what is this phase quantity? So we will see that first. So what are the line quantities and phase quantities? Let's see. So here I have shown you star connection and delta connection. We have two types of arrangement for three phase connections. Okay. So here I will see that what is phase quantity first. Phase quantity means what? The phase quantity means phase voltage and phase current. We will have two types of terms over there. Okay. So phase voltage and phase current means that is associated with that particular phase. Okay, because we are working on three phase means three windings. You can see here winding A, winding B, and winding C. So if some voltage is appearing across this phase, that is called the phase voltage. Okay, so we have some phase voltage of this, some phase voltage of this, some phase voltage of this. And if this is the balance condition, then this phase voltages will be same. Similarly, if I work on delta connection, so the voltage appearing across this winding will be called what? Phase voltage of this, phase voltage of this, phase voltage of this. Right? Now, similarly, in the similar fashion, what will be my phase current? The same current what is flowing through this phase. That is called my phase current. Okay? That is flowing through this winding. That is what phase winding. Similarly, here, if I see this is my phase winding for phase current for this winding, phase current for this winding, and phase current for this winding. Right? So this is the phase quantity that is associated with the particular phase of that winding. Now what is line quantity? Line quantity means that is appearing across two lines. Two lines means these two terminals, that is A, B, C. Okay. So if I talk about the line voltage means the voltage across this terminal A and B. Okay. What is my phase? That is up to this only. So if I see the phase voltage is point A to point N. Okay, but if I say the line voltage, so the line voltage is between point A to point B, then point B to point C, or point C to point A. Okay, similarly here point A to point B is my line voltage for this, then point B to C, and then point C to A. That is my line voltage. And if I see, so this is my line currents, the current which is actually flowing through the outer terminal, outer line. Okay, that is my line current. Here also, this is showing my line current. Okay, so this is the pictorial explanation for what is the phase quantity and what is the line quantity. So now we are going to have the star connection derivation for line and phase quantity relation. So let's see here in the nomenclature that what are the phase quantity and what are the line quantity. Okay, so here we can see that I have given some name. These are my windings A, B, and C, terminals for three windings. Okay, and this is my neutral connection. So what is phase voltage? Phase voltage is the voltage across this winding. Okay, so that winding is connected between point A and point N. So the voltage value is coming as VA. Okay, so this is my first phase voltage value for this star connection. So here we can have the value for phase voltage is VAN. Similarly, I can write the second phase voltage is VBN. Okay, next is VCN. Next is VCN, which is the voltage between terminal C and neutral. Right? So these are the phase values. Now what are my line values? Line values are between this point A to point B. Okay, so this is what the line values. So that name is given as VAB. So this is my VAB, first line voltage. Then next is VBC, and the last one is line, that is VCA. Okay, so these are my line voltages and phase voltages. Okay, so now if I am working on the balance condition, so at balance condition, what should be the condition here? That So at balance condition, what is that? That these all line quantities, that line voltages should be equal in magnitude. Right? We have discussed in the last class that VAB should be equal to VBC should be equal to VC. All the magnitude should be equal. And this is representing my line quantities. So I am representing it with VL, that is line voltage. Okay. Similarly, if I am representing these are my phase values, that is VAL, VBL, and VC. So magnitude of these three voltage should also be equal in balance condition, and this is representing the phase values. So I am representing it as VPS, that is the phase voltage of this system. Okay, so now I have told you what is the line voltage and what is the phase voltage. So first we are going to have the relation between line voltage and phase voltage for star connection. Okay, so let's see that how to go for that relation. So let us start with the relation between line voltage and phase voltage. So for that I have shown here the polarity of the winding, because these are the star connected windings. So the central neutral point has the positive polarity. Okay, this will be positive polarity, and other terminal will be taken as the negative. And here I have assumed that B terminal is negative with respect to A. Okay, so you can have opposite polarity also, there is no problem. According to that, you will have the equation, but the final value will be same. So here, first line, what we are going to have, that is, we are going to apply KVL in loop 1. What is my loop 1? That is this. This is my first loop. Okay, that is from A, B, and A. Okay, so here I have three types of voltage, that is VAB, then VBN, then VAN. Okay, so these three voltages can be taken for this KVL equation. So according to the polarity, here you can check. I have given this equation and written this equation. Okay, you can check the polarity. So what the value I am getting here is VAB equals to VBN minus VA. Right? Now, because we are working on the AC circuit, this is what? This is the vector additions. Okay, this is not the simple arithmetic additions. These are the phasor additions. Okay, and here in the second line, what we see the VAB represents my line voltage. Here, VAB is my line voltage, and VBN and VAN are what? That are the phase voltages. Okay, so this is the relation showing between line voltage and phase voltage, right? But we are not getting the exact relation because this is presenting the phasor addition. Okay, so first we will check that what are the solution for this phasor addition, and then we will have a common conclusion. So let's go for the solution here. Okay, so this is the formula for this, right? We have seen this formula in the school time. So that is what VBN square plus VAN square plus 2VAN VBN cos theta. Now what is this theta? That is theta is the angle difference between VAN and VBN phasor. Okay, so for getting the value of theta, we should have now what is the phasor of VAN and VBN. So let's see first that. So this is the phasor diagram for three-phase values showing. In the introduction class, we have seen that how to draw the phasor diagram for three-phase circuit. So this is showing the phase quantities. Okay, phase voltage, that is VN, VBN, and VBC. All has the same magnitude and equally displaced with 120 degree. Right. Now what should I get? That is the theta angle between VN and VBN. Right. We should always remember that this is not the angle between VN and VBN, not only angle between this. What is that? That is the angle between VBN and minus VBN. Okay, that should be kept remember that VBN minus VBN. Okay, so this is the value showing the VBN phasor. Now what will be my minus VN? If this is the phasor for VN, then this will represent what? That is the minus VN. Right. So now this is minus VA and VB. So what is the angle difference between these two? We have to consider that for this theta. Okay. This is 180 degree. So this is 120 degree, and this complete is 180 degrees. What is the value for theta here? That is, yes, that is 60 degree. So I am getting the value for theta as 60 degree. Okay. So just keep that value here. Now what is VBN and VAN? Here I can see that VBN, VAN are considered as VPH because all the magnitudes are same. Okay, and that is representing my phase quantity. So that is replaced with VPH. Right? So I am replacing that all value in the next line. Now let us see what is the solution here. So the solution is coming as that VBN is replaced with VPH, that is the phase voltage. VN is also same. Okay, as we replace. Now what is theta? That is 60 degree. Now what is the value of cos 60 degree? That is 1 by 2. So that has been cancelled. So we have VPH square. Okay, this can be resolved as root 3 times of VPH. Now what is this? That is VAB. What is VAB? VAB is VN. Okay, so here I can write this as VN. Right? So in general, now we can have a conclusion that the line voltage and phase voltage relationship is like this, that the line voltage is root 3 times of the phase voltage of any of the three-phase system. This is true for all types of three-phase AC system in balanced condition. Okay, so this is VL equals to root 3 VPS. This is very important conclusion for this relation. Okay, here we can have one more thing in the phasor diagram, that the resultant of VBL and minus VL is what? That is VAB. So this is VBL and this is minus VL. So the resultant of these two will be what? The resultant of these two will be, yes, that is VAB. Okay, so that is phasor of phase voltage. So this is the phasor of line voltage. And the angle difference between phase and line voltage is how much? That is 30 degree. Okay, this is 60 degree and this is half of that. That is called how much? That is 30 degree. Right. So in a similar manner, you can apply the same for this second loop or this third loop. Okay. Then you can have a complete phasor diagram for this three-phase system. So let's see what is that. Okay. So this is the phasor diagram we have seen for first loop. Now in this applying the KVL in second and third loop, you can get this type of equation, voltage equation. Okay. That is VBC equals to VCN minus VBA. VCA equals to PN minus VCA. When you resolve this, you will ultimately get the same result, that is VA equals to 3 times of VPS. Okay, you will get the same relation for any of them. Right? So now for phasor diagram, we are going to use this equation. So first equation, that is VAB equals to VBN minus VN, we have already seen. Now second equation, that is VBC equals to VCN minus VB. So let's see what is that. So where is VCN? This is VCN and minus VB means this is VBN. Okay, so you take the minus portion of this. So this is my what? VBN with negative sign minus VBN. Okay, and resultant of these two is what? That is what? The VCB phasor. So this is what the phasor diagram for VBC. Okay, showing the VBC. Right. Similarly, we can have the phasor diagram for third equation also. That is VCA is what? VAN. This is my VAN minus VCA. So this is VCA. So minus of this will be taken like this. This is minus VCA. Okay. And the resultant of this two can be taken as the, yes, that is what? VCA. Okay. This is VCA. So this is the phasor diagram for three-phase balance system showing the line and phase voltages. Right? So here you can see that we are getting the relation between line and phase quantity. The angle difference is 30 degree and magnitudes are line voltage is root 3 times of phase voltage. Okay, so this is about the line and phase voltage relation for star connection. Okay, now in the similar manner we can have the relation for line and phase current also for the star connection. So let's see what is that. So let's see what is the relation between line current and phase current. Okay, so for that I am giving another diagram for star connection that is the similar. Okay, but for the clear vision I am showing in a different diagram. So that is three windings A, B and C at the neutral condition. So what is line current and what is phase current? The current flowing through the phase, okay, flowing through the phase is what? That is the phase current. Right? So suppose this is my IAN, this is my IBN and IC, showing my phase current values. And what are the line currents? The current flowing through the line is what my line current. This is a simple example we have seen at the start. Okay, so these are my line currents. So let me write it here. Okay, so here these are my line and phase currents. That is line current IA, IB, and IC. Phase currents are IN, IB, and IC. Okay, so at balance condition, as we have seen in the voltage, so at balance condition, all the magnitudes of line currents should be equal, and I am going to represent it with IL, that is line current. Okay, and in balance condition, the phase currents should also be equal. So that is IN equals to IB equals to IC. So that is nothing but IH. Okay, so this is the condition. So now in this diagram, you can see that whatever current is flowing through the phase, that same current is going to flow through the line also. Okay, in all the ways. See, this is my phase current, and the same current is going to flow through the line current. Okay, so this is the case. So for star connection, you can directly connect that the current, whatever current I am getting through the phase, that is equals to the line current. Okay, in all the windings, that is IBN equals to IB and ICN equals to IC. Okay, so this is showing what a general expression you can get from here, that is phase current is equals to the line current. There is no change, right? Whatever current I am getting at the phase, the same current I am getting at the line side also. Okay, so this is the relation for phase current and line current for star connection. That's very simple derivation. Okay, but if we will write for the relation for phase voltage and line current, so that is equals to VL by root. So we should remember these two formulas for star connection. Okay, so now I am going to represent this quantity in the phasor diagram. Okay, so this is the phasor diagram for voltage. So in the similar manner, we can draw the phasor diagram for current also. Okay, so suppose this is my phase current, that is IAN. So with 120 degree phase shift, I can have IBN, and another 120 degree phase shift, I can represent IC. Okay, this is the phase currents. Okay, magnitudes are equal and phase difference is of 120 degree. Now, how could we represent the line current here? See, IPH is equals to IL. So this is nothing but IA, that is line current. You can overlap here. This is what IB, line current. Okay, and this is IC, that is line current. Right? So this is the phasor diagram for current phases. This is the phasor diagram for voltage phases. Okay. So after this, we will say that what is the power calculation for this star connection using these two formula. There is two relation between line and phase, current and voltages. Okay. So let's start with that. So let's start with the power calculation. So we know the formula for power, that is VI cos phi. Is which type of power? That is what? Yes, that is the active power. Okay, so we know the formula for active power, that is VI cos phi for single phase AC circuits. Okay, but for three phase, I have three windings, means three phases. Okay, so if I am getting a power for one phase as VI cos phi, so then what will be the power for three phase? That will be, yes, simply that will be 3 times of this VI cos phi. Right, but here we know that this is the phase related quantity, that is representing the power of a phase term. Okay, so this will be what my phase quantities, that is VPH and IPH. These are my phase quantities. But in general, whenever I work, I have the quantities or values for line voltages and line currents. So I should know what is the formula for power in terms of line quantities. So we know that we have the formula for VPH for star connection, that is VL times root 3, and what is IPH for star connection, that is IL. Okay, so power for this can be written as VL by root 3 into IL cos phi. So the relation will come like root 3 times of VL cos phi. Okay, so we should remember this formula, that is in terms of line quantities, line voltage and line current. And when we are using the line quantities, we should have the root 3 term, not the 3 times. Okay, this should be remembered. Now this is the active formula for active power. Now what will be the formula for reactive power? So we can have in the similar manner, that is root 3 times of VL. Sorry, that is VL IL sin phi. Okay, and what is the formula for apparent power? That is root 3 times of VL into. So this is the formula for star connection. Okay, so this is the complete study for star connection. We have seen the relation between the line voltage, phase voltage, line current, phase current, and what is the power calculation, power formula for this three-phase star connected system in balance connection. Okay, so this is all about the star connection. Hope you are getting the understanding. If you have any doubt, you can write in the comment box, right? So that's it for today. Thanks for watching.